vision around the scanning probe microscopy in the future.
Okay, so today we're going to talk about integrating the SPM with other machines, other probes, because just scanning AFM, just scanning NSOM, today it's not enough. We want to have also electrical measurements, we want to have magnetic measurements, we want to know chemical properties, for example, using Raman. So today we want everything to work with as many data as possible at the same time, make us a cup of coffee, publish our article at the same time, and just finish whatever we have to do. So this is what we call a multi-probe system. Now, before I continue with this, I just want to see yesterday if some of the data which I talked about got some clarity. So this also has to do with integrating what we're talking about in the seminar about Raman, so AFM with Raman. So just AFM, not TERS, not NSOM, AFM with Raman has two advantages. One simple advantage is this: we get the topography. We get the topography together with the Raman image, and we get, it's like we can see better what's going on, because just to get a Raman image, the resolution is about 1 micron, and overlaying it, doing a collage with AFM image, we can see better what's going on. A second advantage, which is much more critical, is what we talked yesterday about the AFM feedback. If we have a sample which looks like this, and we're focused on this point and having Raman measurements here, and we're just a regular Raman scanning, no AFM. When the sample will come to this area, this part will be right here. So our focus will be lower than the surface. So the spectrum which we'll get can be a little bit different, especially if we're looking at surface analysis. If, for example, we have 70 nanometers of strained silicon here and the rest is silicon, so it does make a difference where we're focused on. By using AFM together with Raman, so if we have a probe which is now probing at the same focal points, so we have here a probe. So when this area will come here, the whole scanner will come down, and the sample will look like this. So by using AFM feedback, we get also more information and a more correct Raman spectrum. So that's just AFM. There was another thing we talked yesterday about, that's called TERS, which also we integrate with Raman. Now, does anyone remember what TERS stands for? Except for Pierre. Yes. No, you're not allowed to. Okay. Yes, you're good.
Tip enhanced Raman spectroscopy.
Okay, yes. So it's tip enhanced Raman spectroscopy. So we want to enhance the Raman spectrum. Now, this doesn't give us a better resolution of spatial resolution of the Raman, because the Raman, we said the laser beam is about 1 micron, so we'll get with the Rayleigh criterion about a half a micron resolution, more or less. So the TERS won't give us a better Raman resolution. What it will do, it will enhance this spectrum of the chemicals on the surface. Now, how is that done? This is something which I think yesterday wasn't 100% clear. So when we use NSOM, so there's two kind of NSOM probes. One is the aperture and one is the apertureless. The aperture, so with the regular way it's used, we have a laser coming into the probe, which is a fiber, and at the end it's very, very small. Here it's coated with gold, and it illuminates light onto the sample, and let's say it reflects off and we collect it with an objective in the far field. Now, this cannot be done with Raman. Anyone have an idea why we can't, let's say, excite, for example, silicon through a 50 nanometer aperture? We'll get a much better Raman resolution, only a 50 nanometer Raman resolution, and collect that Raman with a spectrometer. Anyone have an idea why that's not possible? Anyone want to guess?
Intensity?
Exactly. Okay, through a 50 nanometer aperture, we cannot illuminate enough intensity to excite the sample to get a Raman spectrum. So what we do is called TERS. It's an aperture-less. So we have here a regular probe, which is not a conducting probe. It's a glass probe, for example. And at the end of it, we somehow glue a small metallic particle, and when the laser, which is coming from above, for example, is exciting the sample, and this metallic particle is near the sample, it will give us an enhancement of the Raman spectrum near the of the chemicals near the surface. So this is called TERS. It's enhancing the Raman spectrum, but it doesn't give us a better spatial resolution. So that's about integrating AFM with Raman. Okay, so we have the topography, we have a better feedback to get a better data of the spectrum, and we have also the tip enhancement. So let's go back to what we call multi-probe systems. So in this system, we see here integrating 4 different probes, 1, 2, 3, 4, and they all can probe a certain surface and get different data. Now, for example, why do we do that? Why is one probe not good enough for us? So here, this is topography of AFM with an AFM probe. The AFM probe, we said the tip of the AFM probe is will give us a resolution of about 10 nanometers, more or less. We can also get better probes. And this is using an NSOM probe. So we're looking here at the fluorescence. The NSOM probe, okay, so we do have, in this case, a laser, which is illuminating the sample, and then we're collecting the light, which is reflecting off the sample with an objective in the far field. And we're looking at the fluorescence of the sample. Now, if we can also do AFM with the NSOM probe, that means this probe, as it's shining, illuminating the laser onto the sample, it's also scanning it as though it's AFM feedback. It's using the way that it knows that it's near the sample, it uses the same feedback as AFM. So we do get additional information of the topography with this NSOM probe. The problem is that this NSOM probe, we said, has an aperture of 50 nanometers, so enough intensity of light can go through it to get fluorescence image, and it's also coated with gold around it, so light won't leak out from the sides. So therefore, the topography, as you see here, you can't really see the same resolution of these small parts on the sample. So what we do with a multi-probe is, with one probe, we excite the fluorescence of the sample, and with another AFM probe, we scan to get a topography, and then we can do an overlay of the fluorescence on the AFM. So therefore, that's one usage of using 2 probes. So this is also another example why we want to use 2 probes. One probe to illuminate and one probe to collect. These are 2 NSOM probes. Here we have the laser going through onto a single mode fiber waveguide. Here we see this is a camera image, optical image looking above. So we have the light going in through here, light coming out of the waveguide, and we're using this second probe to collect the light, and it's going into a detector. And here we have an AFM image with the NSOM image on top of it together. So that's another application of using two probes. Here's also a similar application. We have here one probe which is illuminating a certain waveguide, and another NSOM probe which is scanning this area right here, and we're collecting the light on the waveguide so we can know the properties of this waveguide, how good it's acting. Okay, another similar one. This is just using a much more bigger fiber. So this is also illuminating the light into the waveguide, and the other one is collecting it. Again, another similar one, but here we're not collecting with the aperture probe, but we have here a probe which is aperture-less. So this is glass, and at the end of it we have a metallic small particle, and that is scattering the light which is in the near field. Because here we have plasmons, surface plasmons. By illuminating the laser onto this spot, this creates surface plasmons. That's near field, kind of electromagnetic near field, and it's traveling on a metallic conductor, because the plasmons travel on stuff that are metallic, and this probe has a small metallic particle at the end, and that's scattering those plasmons, and then we can collect them in the far field with an objective. So here, what's also nice about these probes is that we can get them really, really close to each other, because the regular silicon probes, which we see right here, so here's the cantilever, here's the probe, here's the cantilever, here's the probe. We can't really get these two tips of the probes very close to each other. In this case, where we have these glass bent tips, they can get very close to each other. And also they don't block. If we look here from the top, we can't really see what's going on. So here, we're not blocking the optics from above or from below. So to summarize about integrating AFM with our SPM with other systems, we talked about using AFM and NSOM. We talked about one probe of NSOM using to illuminate, another probe for collecting. We talked about electrical measurements. One probe is biased, the other probe is measuring the different electrical properties, or even using 4 electrical probes. We talked about thermal heating. One probe will do a heating at a certain area, and the other probe will scan the thermal conductivity. We talked about integrating inside cryo environments, very low temperatures. Nanolithography together with Raman, nanoindentation, and there's more and more applications of this integrating whatever you can think of. So thank you. If you have any questions,